All right, friends, it's time to do a little MVT analysis. That is the mean value theorem. Here is, simply put, what the mean value theorem says. I'll use pictures here. If you have a function that is continuous between a and b, something like this, and differentiable, that means you can find the derivative anywhere within the open interval, then there exists at least one number, c, such that the slope of the tangent line at c equals the slope of the secant line. I just drew in the slope of the secant line here, or that's the secant line. And the slope is that measurement of rise over run, or the degree in which it's moving up or down. And so there's going to be at least one place, maybe it's right about here, where the slope of the tangent line through it is equal to the slope of the secant line. So here is that purple line, that is the tangent line. And those slopes are parallel, or sorry, slopes are equal, that means those lines are parallel. And so that place where it happens, that means there's a C. It's got to happen at least one time within that interval. So here's how a calculus problem that deals with the MVT goes. This one is you verify that the hypothesis is satisfied and then find that value or values of C that satisfy it. Number 5 says, let's see, f of x is x squared minus x, and in that interval -3 to 5, find that value. Here's what I'd say. You first have to verify the conditions of the mean value theorem. So you'd say f of x is continuous over or on -3 to 5 and differentiable on the open interval -3 to 5. So I can say conditions met. Now, yes, it's a little bit of hand waving, like, wait, don't you have to prove that they are? Here's the thing. This x squared minus x, that's just a polynomial. So it is going to be continuous everywhere. It won't have any jumps or cusps or discontinuities. And if you need to be convinced, let's analyze that a little bit. And I would always suggest to graph that thing if you can. Let's see, x squared minus x, that I can factor out an x, and that's x minus 1. So I know that polynomial, it's a quadratic, and it's going to go through 0 and 1, and it's going to behave something like this, roughly. And we're looking from -3 to 5. This is, again, rough. There's that line through there. That is the point -3. And let's see, at the y-coordinate for -3 is -3 squared minus 3. That's -3, 12. And at the point 5, that's 5 squared minus 5, 25 minus 5, 20. So that sets us up for the mean value theorem. And ahead of time, I see that slope of this line is something like that. Where is that slope going to be the same? It's probably down somewhere here at the kind of close to the vertex. Maybe that's not even there, something like that. So most likely I'm looking for a point somewhere in there. So here's how the mean value theorem works. We've met the conditions, and now the MVT states that there is some number c within the interval -3 to 5 such that the slope of the secant line equals the slope of the tangent line. The slope of the tangent line is f prime of c, And the slope of the secant line is rise over run. F of 5 minus f of negative 3 over 5 minus negative 3. So now we take that starter of the mean value theorem and we work on it. Let's go with the right side first. F of 5 is 20. F of negative 3 is 12. And 5 minus negative 3 is 8. Now f prime of c, let's do a little side work here. F of x is x squared minus x. So f prime of x is just first derivative, 2x minus 1. So f prime of c is just putting a c in for x, 2c minus 1. And what we have here is just an equation to solve. Right side is 20 minus 12, that's 8 over 8, so 2c minus 1 is 8. Oh, no, I'm sorry, 20 minus 12 is 8. 2c minus 1 is 1. So 2c equals 2, c equals 1. That c, looks like there's only one of them, happens at 1. So roughly, here's 1, it's something like that. 1 is that one number where the slope of the tangent line on that function is equal to the slope of the secant line. That's mean value theorem applied.